Hi, everybody. Thank you so much for being here. And thank you, Conf42, for accepting my proposal. The title of my talk is Proactive Cost Management Detecting Anomalies in Logs with Time Series Analysis. Since today's cloud native world, managing cost proactively is more crucial than ever. We will explore how time series analysis, particularly applied to logs, can be useful in this regard. Nice to meet you. Here a little about me. I am Yury Nino. I am cloud application engineer at Google. My passions lie in SRE, DevOps, chaos engineering, and observability, of course, as well as sharing knowledge through reading, writing, and teaching. You can connect with me on LinkedIn, Medium, or X at Yury Nino. My personal webpage is www.yurinino.at. How many of you have been in this situation? Take one moment to think about this. This mimic captures perfectly a common scenario where DevOps teams are asking for more budget from their finance team. That is very common. This is a consequence of misconfiguring cloud computing needs. Let me tell you a sad but unfortunately very common story. It starts with me. Indeed, she is physically similar to me, an on-call engineer constantly battling production issues. Last week, during an incident, I realized a critical flaw. There aren't logs to investigate the root cause of the incident. You can imagine my reaction at that moment. After that, to have to say that it will be impossible to investigate the incident, I decided to activate all available logs, activity, data access, and system events, because that wasn't going to happen me to again. Until here, all was okay, but I got an unexpected consequence. 700% of increment in the billing, all due of activating cloud logs. This story is a perfect example of this quote highlighted by Dr. Matt Dorret, the hidden cost of relying on anomaly-only detection and response systems, which while detecting anomalies is crucial, a reactive approach can lead to significant financial repercussions that aren't immediately obvious. So, what is the true cost of inaction? As you can see from this graph, a lack of proactive cost management can lead to astronomical increases of or in forecasted costs. Like this example showing a 700% increase from April to May. Beyond direct expenses, inaction results in downtime, inefficient resource use, security breaches, and wasted engineering time. The first one related to lost revenue, customer churn, and reputational damage. Inefficient resource use associated to cloud bills exploding was infrastructure. Security breaches when we have massive financial penalties, legal costs, and irreparable harm. And finally, wasted engineering time refers to hours spent troubleshooting reactive problems, similar that the sad story. With this context, here is what I will cover today. I will start by discussing cost management challenges, then explore how logs can be valuable assets despite their complexities. I will then dive into machine learning techniques, but that is an introduction of the machine learning techniques, of course. Specifically, focusing on time series analysis, and I am going to explore practical use cases before opening the floor for your questions. Implementing proactive cloud costs, which involves continuously monitoring, analyzing, and optimizing spending on cloud, it is about preventing instead of reaction costs. The central premise here is that if logs are part of the problem, they also hold the key to the solution. In the context of cloud computing, that is a challenge environment, proactive costs refer to a strategic approach to managing and optimizing cloud spending before it leads to unexpected overruns. And it is mentioned here, it is a critical component to maximize business value from cloud investment while keeping costs under control. Here are more benefits from proactive costs in the cloud context. An important benefit is that it allows us anticipating and preventing issues instead of waiting for cost spikes or resource waste to occur. Another benefits include continuous optimization, predictive analytics, increasing elasticity, choosing the right pricing models, and visibility and monitoring. The first one related to continuous optimization is an ongoing process of refining and improving cloud deployments to maximize resource utilization and achieve business outcomes and the lowest possible price. Predictive analytics that is related to ensure that cloud resources, for example, virtual machines, storage, databases, are properly sized for their actual workloads. And increased elasticity, providing scaling mechanisms to match resource allocation with demand, so you only pay for what you use. Choosing the right sizing pricing models, matching storage classes, and as I mentioned, visibility and monitoring. That is the focus of this talk. However, analyzing logs in the cloud presents unique challenges compared to the traditional environments, like on-premise environment, for example. This is a consequence of distributed, dynamic, and often ephemeral nature of cloud infrastructure, which can make log collection, analysis, and storage significantly more complex and costly. And so we circle back to our core idea. If the problem originates from logs, the solution too should be found within the logs themselves. The challenge is how to effectively extract the solution. With these challenges in mind, the big question remains, what is the solution? How do we can use log data into actionable insights from proactive cost management? A solution lies in SRE anomaly detection. That is a solution because we have another options of solutions in the state of the art. But in this case, this powerful approach combines sophisticated machine learning techniques with statistical methodologies. For example, identifying significant departures from past data, pre-established criteria to pinpoint anomalies. These allow us to move beyond simple thresholds and detect deviations. Here, what is anomaly detection? It is about identifying patterns that significantly deviate from expected behavior, finding the normal abnormal, like for logs, because shift us from reactive firefighting to proactive prediction and give us an early warning system to catch issues before they escalate. By using algorithms that can recognize patterns or anomalies in big data sets, machine learning provides a more advanced method of anomaly detection. The following are important machine learning methods that frequently apply in SRE to anomaly detection. I am going to start with observed-based learning algorithms. In this case, we don't require label data. And considering we don't have classes in cloud logging, it is well situated for anomaly detection applications like this case. Techniques like clustering algorithms and autoencoders fall into this category. The first ones, clustering algorithms, include algorithms that cluster data together based on similarity and recognize outliers as possible anomalies. And autoencoders are models based on networks that can recreate input data. Supervised learning algorithms, another type of machine learning techniques, on the other hand, require historical data with labeled anomalies to train the model. This picture that I make, I can illustrate this concept. Classification algorithms include supervector machines and random forests. And semi-supervised learning algorithms combine elements of supervised and unsupervised learning. Anomalies can be identified by the model, which has been trained on normal data. Isolation forest is a tree-based technique that separates data into subsets in order to isolate the anomalies. Since many SIE measures have a temporal component that is really challenged, use these techniques. So time series analysis techniques are essential for identifying anomalies over time. In seasonal decomposition to find anomalies, time series data is broken down into seasonal, trend, and residual components. I will review more details in the next slides. Let me now talk about how Google manages time series, because Google Cloud offers some services that provides strategies for solving issues related to time series. When dealing with time series, it is important to understand what most are not stationary, meaning their statistical properties change over time. I think that it could be confused since we are not expert in machine learning techniques, but I think that is a good introduction for the topic. And the most important for solving the issue related to predict cost management. For instance, financial time series often exhibit a random walk with drift behavior. Similarly, energy production is heavily influenced by factors like wind and solar supply, leading to dynamic patterns. For solving that, the sad story that I told you, I choose ARIMA model. ARIMA is the acronym of ARIMA. R related to autoregression. The model used the dependent relationship between an observation and some numbers of lagged observations. I integrated, this is the meaning is, it is the first letter in integrated, the use of differencing of raw observations in order to make this time series stationary. And moving an average, the last letters, a model that uses the dependency between an observation and a residual error from a moving average model applied to lag observations. As I mentioned, these time series models are available in Google Cloud, particularly through BigQuery ML. BigQuery ML allows you to create and execute machine learning models using standard SQL queries. I am going to show a demo in which you can see this service and this feature, including to ARIMA, of course. Now, let me explore some real-world examples and use cases where anomaly detection with time series analysis can provide significant value. By using algorithms that can recognize complex patterns, machine learning provides a more advanced method of anomaly identification. The following are important machine learning methods that are frequently applied in SRE to anomaly detection. Time series analysis and anomaly detection have broad application across various industries, but I choose this one, these use cases because they are very challenging and they are in the state of the art of the market. And in retail and e-commerce, they are used for sales and demand forecasting and show rate prediction. Challenges include forecasting new products and complex product hierarchies. Financial services leverage it for asset management and product sales forecasting, despite challenges like noisy data and partially observable markup decision processes. In manufacturing, also, use cases include predictive maintenance and adaptive controls, often facing poor data quality and diverse sensor types. And finally, healthcare, where anomaly detection is used for bed and emergency occupancy and drug demand forecasting, with data privacy and disparate data source being key challenges. This is the architecture of my solution, which includes an input that is basically the logs, which are sent to BigQuery using a log router for the time series analysis. Remember that the proper solution in Google Cloud to analysis the logs using time series is BigQuery ML. Since third-party solutions offer a better visualization of results, I exported the results of the analysis, the time series analysis, to CVS file, which is imported after that is imported in Google Sheet with the aim to visualize the results, as you can see here. Let me show. Now, let me go to the Google console and show you can detect an anomaly in cloud logging using BigQuery at time series. To do this, we are going to create a log sync in cloud logging using the log router option. In this form, we enter the name and a description for the sync. We select a destination, which in this case can be a bucket in cloud logging, a dataset in BigQuery, a bucket in cloud storage, a topic in PubSub, or a separate Google Cloud project. For our exercise, we select the BigQuery dataset, which enable us to create or select the dataset. In this option, we can create the dataset in the local project in a new one or select one that already exists, just what we are going to do in this case. We add a filter to define the logs that we are going to send to BigQuery. In this case, we leave option in blank. And as an optional thing, we can create an exclusion to determine which log records will not be sent to the dataset. With this information, we click on Create Sync and verify this creation. To do this, we are going to BigQuery service and we are going to verify that the table exists. Indeed, the table exists. Now it is time to create the model and detect anomalies in BigQuery. Considering that the log tables has several fields with null values that are not relevant for anomaly detection, we create the model on a subset of the data using this query. As evidenced by the query, we are going using the timestamp of the logs, although we truncate it 2 minutes because it is the thinnest level of granularity that supports time series based on anomaly detection. To have a sample per unit of time, we group the logs by date and severity level, which in this case transform values to integer to facilitate estimation. With this grouping, we can have the associated record count, which we will use the model configuration. What is done? Let's use another query to extract anomalies. Now we are going to download the results to a local file and import them in Google Sheets to have more visualization options. With this done, I generate a chart in order to visualize a possible anomalies. As you can see, the anomalies are here. There are a lot of logs generated in these days, which matches with the behavior in cloud billing. Having this pattern identified, we can predict the next increment in the size of logs and in consequence in the billing.